Problem 41. We've got a logarithmic equation we have to solve. I'm going to change it to exponential. The base of this log is 2. So in exponential form, my base is 2. The exponent is 3 equals 2x minus 1. This is just a simple linear equation. 2 cubed is just 8. So this is just 8 equals 2x minus 1, add 1, 9 equals 2x, and so x equals 9 over 2, or 4.5. Number 42, I'll write it in what we call calculation ready form. This is an exponential equation because of where the x is. It's in an exponent. We name it by where the x is located, or by the degree of the x. In this case, x is in the exponent, so it's exponential. And we solve these by doing the same thing to both sides, which is log them. So I get log 4x, 4 to the x equals log of 83. What that does is allows me to pull the x out front using the laws of logs. Notice I used the logarithm base 10 because my calc will do that. And so dividing by log 4 on both sides, left side it cancels, on the right side I get my answer for what x would be. So you just throw that into your calculator to get a decimal approximation for x. 43 is a very similar problem, except I'd first divide away the 3 out front, and then instead of using log base 10 on both sides, I would use the natural log, like so. And now I'm going to apply that law that says I can take an exponent inside and bring it out front. So now it's x plus 1 ln of e equals ln of 4. This is where the power of taking a natural log of both sides really becomes helpful, because the natural log of e is just asking e to what power gives me e. Well, the answer is just 1, so this is a 1 right there. So now I've got x plus 1 equals ln of 4, and at that point it's pretty easy to see that x is the natural log of 4, and then you subtract 1. So again, our calculator will do a natural log, so you can throw that into your calculator to get a decimal approximation to the nearest hundredths, the third decimal place. Again, no calculator for 44 because I don't have one with me, but the key words here: interest compounded continuously. The amount you'll end up with is equal to your principal times e to your rate times your time. And so if I want to find out how much I'm going to have, I start with my principal, 2,000. I take it times e to the, my rate is 0.08, taking the percent and making it into a decimal equivalent, times 30. I'll put my 30 like that because it's times t. Now that whole exponent needs to be multiplied first. So it's easiest on your calculator to use the e hat, and it'll open a parenthesis, and you just have to type in 0.08 times 30. Then take that times the 2,000, or you can type it all in one statement, and you'll get the value of your $2,000 after 30 years. Alright, 45. This is something we did very recently. Y varies inversely as x means y equals k over x. Says when y is 12, or y is 12 when x is 8. And so k, it looks like, is 96. Let me check that. It says y varies inversely as x, and y is 12 when x is 8. Yep. So k is 96. Just multiplying both sides by 8 right here gives you the 96. So now I've got my relationship between x and y with the k value. Y equals 96 over x. And give me any x and I'll tell you what y is. In this case, it'll tell me x is 20. So y is 96 over 20. You can simplify this. 48 over 10. You can keep simplifying, you can leave it as a fraction, or you could go to a decimal, 4.8. 46, sketch the asymptotes and graph this function. Let's go vertical asymptote at 3 because of the denominator. Looks like numerator and denominator have the same degrees, so 0, y equals 0 is, well, sorry, I made a boo-boo. They have the same degree. We got to look at the ratio of the coefficients of the highest degree terms there. Since they're both x to the first, the y equals 4 over 1, because there's a 1 right there, or just y equals 4 is going to be asymptote right there. And at this point, I'd grab my calculator. We could start cranking through points here, but your calculator is going to give you a really quick idea of what this thing looks like. And that, along with the asymptotes you've drawn in, you should be able to develop a relatively close approximation to what the graph is doing. Problem 47, again, involving these rational expressions. Similar to the previous problem, but this one you have to factor that denominator. Okay, so we'll unfoil it. There's no GCF. 1 and 5 and positive. And what you notice is they have a common factor, so this simplifies to just this expression. Points of discontinuity, -1, can't have x equal to -1, x not equal, or if we want, depending on how it's phrased, what are the points of, or what can x not be. They want what are the points of discontinuity. X equals -1 is a discontinuity, and x equals -5, both from the denominator. X plus 1 canceled out, so there's a hole at x equals -1. There's a vertical asymptote at x equals -5 because it didn't cancel out, and the denominator ends up being of higher degree, so there's a horizontal asymptote at y equals 0. So that kind of sums it all up. Oh, I guess that was 48 I did as well at the same time. 49, simplified state restrictions. Factor your numerator. X and 1 and 5. It's got to be negative. The denominator is a difference of squares. X plus 1s will cancel. And restrictions, so the simplest form, first of all, x minus 5 over x minus 1. Restrictions, x does not equal 1 or -1.